Hello guys, welcome to Self-Help Maths Academy. Today we're going to discuss about the diagonalization of the matrix. Okay, so for this, what is the diagonalization and why we want to diagonalize the given matrix, and is it every matrix is diagonalizable? All these questions will be understood by this particular video. In this, first let us understand the important theorem under the diagonalization, that is called the diagonalization theorem. What it says? It says that an n cross n matrix, capital A, is diagonalizable if and only if capital A has n linearly independent eigenvectors. Okay, so what is the meaning of this? It means that if you have, suppose, 2 cross 2 matrix, and this matrix is diagonalizable if and only if it has two linearly independent eigenvectors. It should have two linearly independent eigenvectors. So linearly independent, you know that it should have a trivial solution. So whenever you have the two linearly independent eigenvectors, then 2 cross 2 matrix will be diagonalizable. If you have linearly dependent, then that particular matrix is not diagonalizable. It is not diagonalizable. Okay. Suppose you have got a 3 cross 3 matrix, then it must have a 3 linearly independent eigenvectors, and so on and so forth. Okay, so that means what? In general, if it is n cross n matrix, then it must have n linearly independent, which is very important. If you have linearly dependent vectors, then we say that that particular matrix is not diagonalizable. Okay, that I think we will see it with the help of example. So in fact, what you do is we are trying to write our A as P D P inverse. So here we'll try to write our A as P D P inverse, where D is the diagonal matrix. It is a diagonal matrix. I'll explain all this. A diagonal matrix. If and only if, when we say it is a diagonal matrix, if and only if your P, the columns of the P, the columns of the matrix P are n linearly independent eigenvectors. Linearly dependent eigenvectors of the matrix A, and P inverse is the inverse of matrix P. Okay, so in this case, the diagonal entries of D, these diagonal entries of D are the eigenvalues of the matrix A. Okay, they corresponding to respectively to the eigenvectors of the matrix P. That I will also show you with the help of example when we are solving. This is one particular theorem. Another theorem says that an n cross n matrix with n distinct eigenvalues is diagonalizable. So in this case, what we are trying to say, if you have a 3 cross 3 matrix or 2 cross 2 matrix, in general, if you have a n cross n matrix, if you have n distinct eigenvalues, for example, you have got a 2 cross 2 matrix, and suppose it has eigenvalue as, say, lambda is equal to 1 and lambda is equal to, say, 3. If you see here 1 and 3 are distinct eigenvalues, then that 2 cross 2 matrix will become diagonalizable. So that this is like compulsory. So sometimes you will also see some of the examples when we have solved in the previous videos, where you have seen the eigenvalues are having a multiplicity 2, which is repeating 2 times, which is repeating say 3 times if it is 4 cross 4 matrix, like that. So in such cases, it is different thing. But if you have all the 3 eigenvalues are different in, say, 3 cross 3 matrix, then it is diagonalizable. In 2 cross 2 matrix, in both the eigenvalues are different, they are distinct, then it is diagonalizable. That is the simple meaning of this particular theorem. Okay, now straight we will go to the diagonalization process, and we will try to understand what are the steps we involve in the diagonalization. So step number 1, what we do? Okay, they give you the matrix and they ask you to check whether it is diagonalizable or not. So first step, we have to find the eigenvalues. If the matrix A is given to you, find the eigenvalues of A. That is your first step. Step number 1. Step number 2. Once you find out the eigenvalues of A, we have to find out the corresponding linearly independent eigenvectors of A. Okay. Finding the corresponding linearly independent eigenvectors of A. This is your step 2. Then step 3. In step 3, what we do? We construct the D from the corresponding eigenvectors. Construct the matrix D, that is the diagonal matrix, from the corresponding eigenvalue. From the corresponding eigenvalues. Okay. And then you will finally write your A as PD P inverse. So that's how we will actually have these steps. So let's start with the first step, and we will take the example and we will try to understand in detail with the help of example. So the example is diagonalize the following matrix if following matrix diagonalize the following matrix if possible. Okay, let's see how do we do it. So here what is the matrix is given is, the matrix given is, say, A equal to 1 3 3 minus 3 minus 5 minus 3 3 3 1. This is our given matrix. Okay, so here what we have to do, we have to find out the invertible matrix P which diagonalizes the given matrix A. Okay, let's do this step by step now. So we will find the eigenvalues of the A in the first step. So we know that the characteristic equation of the matrix A is given by determinant of A minus lambda I, which is equal to 0. Let's find out the characteristic equation of this particular matrix. 1 minus lambda, 3 3 minus 3 minus 5 minus lambda minus 3 3 3 1 minus lambda. This is equal to 0. Okay, so now let us solve this particular matrix in order to find out the characteristic polynomial first. So this is like 1 minus lambda into minus 5 minus lambda into 1 minus lambda. So minus of minus, it is plus 9 here. Then minus 3 into, we have minus 3 into 1 minus lambda, minus of minus, that is again plus 9. So this is plus 3 into, okay, here we have got minus 9 minus 3 into minus 5 minus lambda. Okay, minus 5 into minus lambda, which is equal to 0. Let's do this is now 1 minus lambda into, so solve this. Here minus 5 into 1, which is minus 5 plus 5 lambda minus lambda plus lambda square plus 9, minus 3 into minus 3 plus 3 lambda plus 9 plus 3 into, here it is minus 9 and minus 3 into 5, which is 15, minus 3 into minus lambda, that is plus 3 lambda. Okay, which is equal to 0. which is equal to 0. Okay, now let us solve it further. Here we get 1 minus lambda into this is lambda square minus plus 5, this is 4 lambda, and this will be plus 4 minus 3 into 3 lambda plus 6 plus 3 into 3 lambda plus 6 is equal to 0. Okay, yeah. So here I can take this 1 minus lambda inside and we can solve it further. So I'll multiply this with lambda square, 1 with lambda square, 1 with the whole thing here, then with negative lambda it is negative lambda cube, then negative 4 lambda square, then negative 4 lambda. Multiply this with negative 3 here, this is minus 9 lambda minus 18 plus 9 lambda plus 18, this is equal to 0. Now let's see what all the things we can cancel first. So plus 18 is there, minus 18 is there, plus 9 lambda minus 9 lambda, minus 4 lambda plus 4 lambda we have. So we are left with now minus lambda cube. Okay, minus 4 lambda square plus lambda square is minus 3 lambda square, then we have plus 4 equal to 0. Okay, so I can just take that lambda negative sign both the side. So lambda cube plus 3 lambda square plus 4, which is equal to 0. Okay, now by the inspection method, let us find out first what value will make this element, this whole thing as 0. What if I take lambda equal to 1, lambda equal to 1, then this becomes 1, this is 3, sorry, this will be minus 4 here. Let me change it as I take the negative sign. As I take the negative sign out, it is negative 4 here. So if I take the 1 lambda equal to 1 value, this will become 0. So therefore lambda equal to 1 will become one of the solution of this particular equation, right? So therefore what we do, we'll try to use the by finding out the division method. So let us find out another remaining roots, 3 lambda square minus 4. So this we divide it by lambda equal to 1. When lambda equal to 1 means lambda minus 1 will become the root, right? Lambda minus 1 will become a root. So let's divide this with lambda minus 1. So here we have lambda cube. So this is lambda square. This is lambda cube here. Minus 1 into lambda square is minus lambda square. Okay. So change the sign, minus and plus, this cancels. So here we have got 4 lambda square minus 4 lambda, and here it is 4 lambda square. So I'll multiply with 4 lambda. So this will be 4 lambda square minus 4. Okay, this change the sign again, minus and plus. So this will be 0 here. So here we have got this as lambda square plus 4. Let me check. Oh, sorry, I have to. This one is lambda square plus 4 lambda we have. Okay, let me solve it here. So here we have got 4 lambda, I'm sorry. So here what we have, this is like now 4 lambda. Let me erase it. Okay, so we have to, when we are doing, we have to be very careful. That's what I'm saying. Even I should not do the mistakes. So here we have got minus 4 lambda minus 4. So therefore I have to multiply with 4 here. So this will be like 4 lambda minus 4. Now we have got 0. Okay, so here we have got the factors as lambda square plus 4 lambda plus 4. Okay, and we have also already have a factor called lambda minus 1. So let's find out the values for this one. This is simply lambda plus 2 the whole square. This one, this particular equation, quadratic equation, give us the lambda value as 2, lambda plus 2 the whole square. So this implies what? This implies we have got lambda equal to 1 with multiplicity 1, and lambda plus 2 the whole square is, this is nothing but lambda equal to negative 2 with multiplicity. How many times it is repeating? 2 times. So with multiplicity 2. So these are the eigenvalues we have got. This is our first step. So here we are good that we have found the eigenvalues with respect to the matrix A. Okay. Now what we do, we try to find out the, now let's start with the step 2 where we have to find out the finding the linearly independent eigenvectors. Okay. So step 2, finding the three linearly independent eigenvectors. Okay. So let's find out now. How do we, because we need the three linearly independent eigenvectors since it is a 3 cross 3 matrix. So this is a very critical step. Okay. So very critical step, and if it fails, then diagonalization theorem says that A is not diagonalizable. So this is very critical steps in order to find out the linearly independent eigenvectors. Okay. So since it is 3 cross 3 matrix, we need to find out three linearly independent eigenvectors. And now let's see, for lambda equal to 1, we have the lambda equal to 1. We know that it should be ax should be equal to 1 into x, this format, and then it is like ax minus 1 into x is equal to 0. This implies nothing but what, a minus I, where I, like lambda is 1, so therefore it is simply a minus I. We have to argument with 0. So this is our matrix we need to consider. So this is like a minus I, which we have to argument with 0. So this is now, so this is like 1. Let me take from the diagonal entries, let me take this as 1 minus 1. Then we have 3 minus 3 minus 5 minus 1 minus 3. This is 3 3 1 minus 1. Okay, argumenting this with 0. So this will give us, here it is 0 3 3 minus 3 minus 6 minus 3. This is 3 3 0. Okay, so 0 0 0. Okay, yeah. Now we have this one. Let me, since in the first entry we have 0, so what I'll do, I'll try to interchange our R3 and R1. R3 and R1. So we will get here 3 3 0 0 minus 3 minus 6 minus 3 0. This is 0 3 3 0. Okay. Yes, now what we do, we have to make, with the help of this is already 0, so hence we have to make only this element 0. So R2 changes to R2 plus R1. What we get here 3 3 0. This is 0, and then minus 3 plus 3 is 0, minus 6 plus 3, that is minus 3. This is minus 3. This is 0 and 3 3 0. Okay. Now with the help of R2, you can see, with the help of R2 we can make this element 0. Therefore R3 changes to simply R3 plus R2. We will do, we will see what we will get here. We will get 3 3 0 0 minus 3 minus 3 0 0 0 0 0. Okay, yeah. Now I think we are good here. So let me like from here we will write it as a solution. For still what we do is from R1 1 by 3 times of R1, from R2 minus 1 by 3 times of R2. Let's do this one more step in order to 1 1 0 0 1 1 0 0 0, this with 0 0 0. Okay, now let's write this as a solution, like x1 plus x2 equal to 0. Here it is x2 plus x3 equal to 0, and from here if you see 0 equal to 0 means x3 is free. X3 is free variable. So hence we will write this one. From here your x2 is negative x3. Your x2 is negative x3. We have got x2 as negative x3. So substituting this value in the first equation, we will get here x1 equal to negative x2, and x2 is nothing but negative x3. So this will be negative times of negative x3 This is x3. Okay, so we have got x1. We have got x1 as x3 and x2 as negative x3. Since x3 is free, x3 will be x3 only. So now let's write this as a solution. We will get x as x1, x2, x3. So this is x1 is what? X1 is x3. X3 is negative x3 and x3 is free, so it is x3 only. So if I take x3 out, so this is 1, negative 1, 1. So this is our one of the vector. Okay, this is our one of the vector which is corresponding to lambda equal to 1. Lambda equal to 1. We have got one vector. Now we have got lambda equal to next one. We have got lambda equal to, for lambda equal to negative 2, let's find out the eigenvector. So for lambda equal to negative 2 means it is ax equal to negative 2x. This implies ax, if I take on this other hand, it will become ax plus 2x equal to 0. This implies a plus 2i times of x equal to 0, or it is simply, you can have it as a plus 2i augmenting this with 0. Okay, so this is the matrix which we require. So for every matrix, when you are solving the example for a eigenvector, you need to do this. Now let's do this for the given matrix. We have a plus 2i, so it is like from the diagonal entries we need to add plus 2. So 1 plus 2, 3, 3, minus 3, minus 5 plus 2, minus 3, 3, 3, 1 plus 2. This is 0, 0, 0. Okay. Yes, now this is equal to 3, 3, 3, 0, minus 3, minus 3, minus 3, 0, 3, 3, 3, 0. Yeah. So here what we do, if you observe carefully, from our with the help of R1, R2 changes to R2 plus R1, R3 changes to R3 minus R1. So this gives 3, 3, 3, 0. This is 0, 0, 0, 0, 0, 0, 0 and 0. So from here we have got clearly two free variables. Okay, x2 and x3. So what I'll do here is from R1, 1 by 3 times of R1 we do, and we get it as 1, 1, 1, 0, 0, 0, 0. Okay, yeah. Now let's write it as a solution. We will write x equal to, here if you write the solution, it will be like x1 plus x2 plus x3 equal to 0. So since x2 is free and x3 is also free. If you remember, lambda equal to 2 was lambda equal to negative 2 was having a multiplicity 2. That's the reason we have got two free variables here. Okay, so here we'll write x1 as negative x2, negative x3, and x2 is free and x3 is free variable. So when you write it as a solution, x will be equal to x1, x2, x3. This is equal to x1 is negative x2, negative x3. x2 is x2, x3 is x3 because they are free variable. Now this we can write it as x2 into. So in this negative 1, here it is 1 and there is no x2 terms. So plus x3 into, in the first case it is negative 1, in the second it is 0, in the third it is 1. So this is V2, this is V3. Okay. Now what we have got with respect to lambda equal to negative 2, we have got V2, the two vectors, minus 1, 1, 0 and V3 equal to minus 1, 0, 1. So as you just go on changing the value of x2 and x3, you'll get infinitely many eigenvectors, but we are using one eigenvector as V2 and V3. Alright. So we have got now two like linearly independent eigenvectors. So here you can just check if you want that they're clearly linearly independent, so no need for clarification, but still I'll write them as in the format like v1, v2, v3. That means my v1 was with corresponding to the eigenvalue lambda equal to 1, for lambda equal to 1, and these v2 and v3 are corresponding to lambda equal to negative 2. In that format only I'm writing. This is very important because what format you are using it to form your P, because this is your P now. Whatever the format you're using it to find out the P, I mean like writing the P, the same format you should use it for writing the constructing the D. Okay, so now I'm using the format as first I'll use the lambda equal to 1 eigenvector. So lambda equal to 1 eigenvector, corresponding eigenvector is here. For lambda equal to 1 we have got, yeah, we have got here, this is our lambda equal to 1 for corresponding this eigenvector is here 1 negative 1 1. Okay, so let me write that 1 1 negative 1 1. This is our eigenvector corresponding to lambda equal to 1, and the remaining eigenvectors just now we found, these are our remaining eigenvectors minus 1 1 0 minus 1 0 1. So these are the two different eigenvectors which are corresponding to lambda equal to 2. Okay, so this is the step 3. This is actually, you can write it as step 3. This is your step 3 where you're constructing the matrix P, constructing the matrix P. And please make sure that this is with respect to lambda equal to 1 and these two are with respect to lambda equal to negative 2. Why I'm saying it again, because whatever the format you're taking, okay, I mean the way you're writing your P. For example, here if you use or if for example you're written your P as, like say first you have taken this lambda equal to negative 2 minus 1 1 0 minus 1 0 1, and then you've taken last one 1 negative 1 1. Okay, if this way you've taken, where first you're taken for lambda equal to negative 2, then you're taken for lambda equal to say 1, then we have to use the same format for constructing the D. That's why I'm saying that you have to clearly it is very essential to follow the order of the eigenvalues that matches the order which you chosen it to construct the P. Okay, that's why I'm telling it's very important to remember the order which you are following for constructing your P. So step number 4. Now if I'm choosing this one to construct the P, okay, so then our D should be construct here, the D should be the step 4 is construct D from the corresponding eigenvalues, okay, corresponding eigenvalues. So here I'll write one important step, that is in this step it is clearly essential that the order of the eigenvalues matches the order chosen for constructing the D. Okay, okay, let's see D will be now, as I told you, first P was related to lambda equal to 1, so therefore my diagonal entry, this is my 1, lambda equal to 1, remaining values I'm writing 0, then 0, the next diagonal entry should be negative 2, because this lambda equal to negative 2 is our next eigenvalue. So 0 0 negative 2. You see this is with respect to lambda equal to 1, lambda equal to negative 2. Okay, so this is a good idea to check whether P and D are really works. For that, simply a simple way of checking, is instead of checking like A is equal to P D P inverse, we can simply check this as whether A into P is equal to P into D or not. Okay, so just take your A into P, take your A into P, and then take a P into D. Like say if I take A into P, so 1 3 3 minus 3 minus 5 minus 3, this is 3 3 1, and your P with the order, so 1 minus 1 1 and minus 1 1 0 minus 1 0 1. Okay, so this is your P which you have constructed just now. So this is 1. Now multiply this one, because both are 3 cross 3 matrix. I'm just multiplying this with row in the column. So 1 minus 3 plus 3. So this is minus 1 plus 3 and 0. So this is minus 3, 0, plus 1. Okay, this one is minus 1, minus, sorry, here we have to, here we did a mistake. So this is minus 1, 0, plus 3. Yeah. Okay, next one, similarly you do this row with this column. So this you will get here minus 3, plus 5, minus 3, minus 3, sorry, plus 3, minus 5, 0, then 3 plus 0, minus 3. Okay, then this is 3 minus 3 plus 1, and then you have got minus 3, sorry, minus 3 plus 3, minus 3 plus 3 plus 0, minus 3 plus 0 plus 1. Okay, so after solving you get here finally 1, 2, 2, minus 1, yeah, minus 1, minus 2, 0, then this is 1, 0, minus 2. So this is your A into P. Okay, let's find out P into D now. Similarly, P into D, this is optional, but it is very good, and it's actually a good idea to check whether our constructed P and D are really working or not. So this is like 1, minus 1, minus 1, minus 1, 1, 0, then 1, 0, 1. Okay, so this is our P into D. We have to find out our D. 1, 0, 0, 0 minus 2, 0, 0, 0 minus 2. Okay, let's find out this one. Like again you multiply this one, we will get 1, this is 1, simply 1, because remaining all the elements are 0. The second one is 1 into negative 2, it is simply 2, and this is we have got 2 again. This is, yeah, this is minus 1, remaining all elements are 0. This is negative 2, remaining all elements are 0 here. This is 1 simply, then here it is 0, 0, and then here we get 0 plus 0 minus 2. Yeah, so if you see, it is like, you know, from comparing the AP and this one, they are one another same. So therefore it is correct that whatever we have got our A equal to PDP inverse, this is like our matrix A is what? Diagonalizable. So these are the steps, guys, we have to follow when we're solving the diagonalization. Okay, so what we have done in the first step, we have found the eigenvalues. In the second step, we have found the corresponding eigenvectors. In the step 3, we constructed the in the step 3 we constructed the matrix P, and it's very important. Second step is critical step. Here if you get the eigenvectors properly, if it is a 3 cross 3 matrix, if you get 3 eigenvectors, it is correct. If you're getting 2, then it is not diagonalizable. No need to go for the third step. Once you get the corresponding eigenvectors in the second step, we have to go and construct the step 3, constructing P. And here what is important is what is the order you are following. Here any order for construction of P, there is no mandatory or essentiality that you have to follow the same order. You may take, like as I told you, you may take lambda equal to negative 2 first and then lambda equal to 1 next, or lambda equal to 1 first and lambda equal to negative 2 first. Okay, this is how you can follow the order, but make sure that what order you are following for P, same order you must follow it to construct the D. That is very important. Okay, so here it is the following the order is not important, but in D, in construction of a diagonal matrix, we must follow the order of the matrix P, what you constructed. Okay, that is very important. So once you construct your matrix D, it is almost we are done, but we have to verify whether whatever the construction of D and P we have got, is it right or not. For that, a simple checking, that is multiply the given matrix A with the P and then P with D. If you are getting the same answer, then whatever whatever P and D we have constructed, it is correct. Okay, so that's the answer, guys. I think that's how you'll be doing the diagonalization. I think now I'll give you one example, so try and just check whether it is diagonalizable or not. Okay, answer me in the comment. If it is diagonalizable, say diagonalizable. If it is not diagonalizable, not diagonalizable, say non-diagonalizable. Okay, the given matrix A, just check whether it is diagonalizable or not. Okay, minus 4, minus 6, minus 3. So this is the one. Yes, this is the one. So please check and comment in the box whether it is diagonalizable or not. Okay. Okay, then I think with this we'll conclude today's discussion, guys. Maybe in the next video we will come up with the next topic. Till then, take care, guys. Bye bye.